close your eyes. Tonight, I want you to imagine two identical machines, built in the same room, assembled by the same hands, tested by the same engineers, loaded with the same instruments, the same cameras, the same golden records carrying the sounds and music and greetings of a small blue world. Two machines, as alike as twins, sitting side by side in a clean room in Pasadena, California, in the summer of 1977. One of them would become the most famous spacecraft in human history, the farthest object ever made by human hands. The first to cross the boundary of the solar system and enter interstellar space. Its name would be known by schoolchildren and scientists alike. It would be the subject of documentaries and books and songs and poems. It would carry a photograph of Earth, a pale blue dot that would change the way an entire species thought about itself. That was Voyager 1. The other twin was identical. Same design, same instruments, same golden record, same nuclear power source slowly decaying inside its body. But this twin took a different path, a longer path, a path that no spacecraft had ever taken before and that no spacecraft has taken since, a path that carried it past not 2 but 4 giant worlds, through encounters so extraordinary that they rewrote our understanding of the outer solar system, and then the world forgot about it. This is the story of Voyager 2, the forgotten twin, the spacecraft that did something that Voyager 1 never did, something that no machine in history has ever done, and something that no machine currently planned or funded will do again in your lifetime. Voyager 2 is the only spacecraft ever to visit Uranus. Voyager 2 is the only spacecraft ever to visit Neptune. Voyager 2 is the only spacecraft in history to have visited all 4 of the giant outer planets of our solar system: Jupiter, Saturn, Uranus, and Neptune. It completed the Grand Tour, a journey that was supposed to be impossible, through a window in the alignment of the planets that opens only once every 175 years. It flew that corridor perfectly, using the gravity of each planet to sling itself onward to the next, gaining speed from each encounter, falling deeper and deeper into the outer solar system, farther and farther from home, until it reached the last giant world, a blue jewel of ice and wind at the very edge of the planetary system, and photographed it in a way that no telescope on Earth had ever been able to. And then it kept going, past the last planet, past the last moon, past the last icy body at the edge of the solar system, into the void, into the dark, into interstellar space. Voyager 2 is out there right now. At this very moment, as you settle into bed and let the weight of the day leave your shoulders, a small machine is drifting through the space between the stars, roughly 137 astronomical units from the Sun. That is, nearly 12.5 billion miles from Earth. The signals it sends back, traveling at the speed of light, take more than 19 hours to reach us. It is the second farthest human-made object in existence. Only its twin, Voyager 1, is farther away. And yet, in many ways, Voyager 2 had the more remarkable journey. It saw more. It discovered more. It went places that its twin could not. And it did all of this with technology from the 1970s, a computer with less memory than a modern wristwatch, and a nuclear power source that was slowly dying from the moment it was switched on. Tonight, we are going to follow Voyager 2 on its entire journey. From the warm, Florida morning when it climbed into the sky on a column of flame, to the frozen surface of Neptune's captured moon, to the boundary of interstellar space where the sun's breath finally gives way to the galactic wind. We are going to visit every world it visited, see everything it saw, understand what it found and why it matters. This is a story about a machine. But it is also a story about ambition, about the audacity of sending something so small into something so large. It is a story about luck, because Voyager 2 survived things that should have killed it, not once, but many times. And it is a story about time, about what it means to build something that will outlast not just its creators, but their entire civilization. Let us begin in the way that Voyager began, with a window in the sky that was about to close and a small group of people who refused to let it. Before we continue, I want to take a moment. If you enjoy falling asleep to these journeys through the cosmos, consider subscribing to the Science Pillow. Every week, a new documentary arrives designed to carry you gently through the wonders of the universe and into a peaceful sleep. All you need to do is press the subscribe button, and the stars will be waiting for you every night. You do not need to stay awake. You do not need to take notes. Just lie back, close your eyes, and let the universe do the rest. Now, let us go back to 1977. Section 2. The Alignment of Worlds. In the late 1960s, an aerospace engineer at the Jet Propulsion Laboratory named Gary Flandreau was given a seemingly straightforward assignment. He was asked to study possible trajectories for missions to the outer planets. It was the kind of work that fills notebooks with equations and orbital diagrams, the kind of work that most people would find numbingly tedious. But Flandreau was about to stumble upon something extraordinary. As he plotted the positions of Jupiter, Saturn, Uranus, and Neptune for the coming decades, a pattern emerged. In the late 1970s and early 1980s, the 4 giant planets would be arranged in a roughly geometric arc on the same side of the Sun. Not clustered together, they were still separated by hundreds of millions of miles, but arranged in such a way that a spacecraft launched from Earth at the right time, on the right trajectory, could use the gravity of each planet to redirect itself toward the next. Like skipping a stone across a pond, except each skip would carry the stone farther and faster than the last. This alignment is sometimes called the Grand Tour configuration, and it is extraordinarily rare. The 4 outer planets orbit the Sun at different speeds and different distances. Jupiter takes about 12 years to complete one orbit. Saturn takes 29 years. Uranus takes 84 years. Neptune takes 165 years. For all 4 to align in a configuration that permits this kind of multi-planet trajectory, you need to wait a very, very long time. The answer turns out to be roughly 175 years. The last time the planets were in a similar configuration was during the presidency of Thomas Jefferson in the early 1800s. The next time, after the 1970s window, would be in the 2150 range, more than a century and a half away. If humanity missed this window, no one alive in 1977 would live to see the next one open. Flandreau understood the significance of what he had found. He was looking at a once-in-a-lifetime opportunity. More than that, a once-in-multiple-lifetimes opportunity. A corridor through the outer solar system that the planets themselves had opened briefly and that would close again before the century was out. The Grand Tour concept was ambitious from the start. The original proposal called for large, sophisticated spacecraft that could survive the entire journey from Jupiter to Neptune, a trip lasting more than a decade. But the early 1970s were a difficult time for NASA's budget. The Apollo program had consumed enormous resources, and Congress was in no mood to fund another expensive space adventure. The Grand Tour proposal was rejected in favor of something smaller, cheaper, and less risky. What emerged from those budget constraints was the Voyager program. 2 spacecraft instead of the proposed 4 or 5, each designed to visit Jupiter and Saturn as the primary mission, with the possibility of continuing to Uranus and Neptune built into the engineering, but not officially funded or promised. If the primary mission succeeded and the spacecraft survived, NASA could decide later whether to extend the mission to the ice giants. But there were no guarantees, no commitments, no promises beyond Saturn. This is one of the most remarkable aspects of the Voyager story. The Grand Tour, the complete circuit of all 4 giant planets, was never the official mission. It was an aspiration, a hope, a possibility that the engineers quietly designed for while the bureaucrats approved something more modest. The spacecraft were built strong enough to survive the full journey, equipped with enough fuel and flexibility to navigate the complex multi-planet trajectory, and programmed with computers that could be reprogrammed from Earth as the mission evolved. All of this was done with the tacit understanding that if things went well, the real mission, the one everyone secretly hoped for, would begin after the official mission ended. The 2 Voyager spacecraft were assembled at the Jet Propulsion Laboratory in Pasadena, California, in the mid-1970s. They were identical in design, a 10-sided aluminum bus about the size of a large desk, bristling with instruments and dominated by a white high-gain antenna dish 12 feet in diameter. 3 long booms extended from the central body, one carrying the magnetometer sensors, one carrying the science instruments, and one carrying the 3 radioisotope thermoelectric generators that provided the spacecraft's electrical power. The power source deserves special attention because it is both elegant and haunting. Solar panels, which work well for spacecraft near the Sun, are useless in the outer solar system. At Jupiter's distance, sunlight is only about 4% as intense as at Earth. At Neptune, it drops to roughly 0.1%. The Voyager engineers needed a power source that did not depend on the Sun. They chose nuclear decay. Each Voyager spacecraft carried 3 RTGs, radioisotope thermoelectric generators, containing cylinders of plutonium-238. This isotope is not the same as the plutonium used in nuclear weapons. Plutonium-238 generates heat through radioactive decay, and that heat is converted into electricity by thermoelectric elements. No moving parts, no combustion, no chemical fuel that can run out. Just the steady, patient, inevitable disintegration of unstable atomic nuclei, releasing energy atom by atom, decade after decade. At launch, Voyager 2's RTGs produced about 470 watts of electrical power, enough to run perhaps 4 or 5 household light bulbs. The entire spacecraft, all its instruments, computers, heaters, motors, and radio transmitter operated on less power than a typical hairdryer. But plutonium-238 has a half-life of 87.7 years, which means the power output drops by roughly 4 watts every year. By the time you are hearing this, nearly 5 decades after launch, the RTGs are producing only about 220 watts, and the number continues to fall. The spacecraft is dying, slowly, gently, the way a campfire dies when no one adds more wood. The glow fades. The warmth retreats. One by one, instruments are shut down and heaters are turned off, like rooms in a house being closed for the winter. And eventually, probably in the mid-2030s, the last instrument will fall silent, the transmitter will fade to nothing, and Voyager 2 will become what it was always destined to become, a silent machine drifting through interstellar space, carrying a golden record that no one may ever play. But we are getting ahead of ourselves. Before the silence, there was the launch. Before the darkness, there was a bright Florida morning. Before the end, there was the most extraordinary beginning in the history of space exploration. On August 20th, 1977, a Titan 3E Centaur rocket lifted off from Launch Complex 41 at Cape Canaveral, Florida. The rocket climbed slowly at first, balanced on twin solid rocket boosters and a central liquid-fueled core stage, rising through the warm, humid air of the Florida coast with a roar that could be heard for miles. Strapped to the top of that rocket was Voyager 2. Despite its name, Voyager 2 launched first, 16 days before its twin. The naming was based not on launch order, but on trajectory. Voyager 1, launching later, would take a faster path to Jupiter and arrive first. Voyager 2 would take a slower, more leisurely route, one that would carry it past Jupiter and Saturn, and then, if all went well, onward to Uranus and Neptune. The launch appeared to go smoothly from the outside, but the engineers inside the control room knew better. There were problems. The Titan booster experienced a roll anomaly during the first few seconds of flight that came dangerously close to exceeding the rocket's structural limits. The guidance system compensated, barely, and the rocket continued climbing. Then, during upper stage separation, a brief electrical anomaly caused a moment of terror among the controllers. The spacecraft's instruments detected unexpected vibrations, and for a few agonizing seconds, it was not clear whether Voyager 2 had survived the separation intact. It had. But the launch was a harbinger of things to come. Voyager 2 would be plagued by technical problems throughout its mission, far more than its twin. Its primary radio receiver failed just months after launch, forcing engineers to rely on a backup receiver that had its own issues, a stuck capacitor that made it unable to track frequency changes accurately. This meant that every command sent to Voyager 2 had to be precisely tuned to a fixed frequency, accounting for the Doppler shift caused by the spacecraft's motion and the Earth's rotation. A mistake of a few hertz could mean the command would be missed entirely. The stuck receiver was a problem that should have been mission-ending. In the early days, many engineers feared it would be. But the team at the Jet Propulsion Laboratory adapted. They developed new procedures for commanding the spacecraft, calculating the Doppler shifts with painstaking precision, timing their transmissions to coincide with moments when the frequency offset was minimized. It was an exercise in ingenuity born of desperation, and it worked. For the next 40-plus years, every command sent to Voyager 2 had to account for that stuck capacitor. Every instruction had to be perfectly calibrated. One mistake, one miscalculation, and the spacecraft would go deaf. There was another problem. Shortly after launch, the spacecraft's scan platform, the motorized mount that aimed the cameras and other remote sensing instruments, showed signs of sticking. The platform could pan left and right and tilt up and down, allowing the instruments to track targets during planetary flybys. If the platform failed, the cameras would be locked in one position, unable to aim at the moons and ring systems that were the primary targets of the mission. Engineers spent months studying the problem from Earth, sending test commands, analyzing the platform's behavior, developing workarounds. They concluded that the lubricant in the platform's actuator had partially solidified in the cold of space, causing increased friction. The solution was counterintuitive. They would move the platform more, not less, to work the lubricant back into a functional state. Over time, the platform loosened up enough to function reliably, though the engineers would remain nervous about it for the entire mission. These early problems established a pattern that would define Voyager 2's journey. The spacecraft was, in some ways, the scrappier twin. Where Voyager 1 cruised through its mission with relatively few technical issues, Voyager 2 seemed to invite them, and each time, the team on the ground found a way to adapt. They patched and improvised and recalculated and reprogrammed, turning a spacecraft with broken hardware into one of the most successful explorers in the history of science. There is something deeply human about that. About building something, sending it into the void, watching it break, and then figuring out, from billions of miles away, how to fix it. About refusing to give up. About treating every failure not as an ending, but as a problem to be solved. The engineers who nursed Voyager 2 through its ailments were not just doing their jobs. They were engaged in an act of devotion. They loved that machine, and they kept it alive through decades of trouble and distance and silence because they understood what it was doing and where it was going and why it mattered. And so Voyager 2 flew outward, past the orbit of Mars, past the asteroid belt, that broad, sparse ring of rocky debris between Mars and Jupiter, where millions of fragments orbit the Sun, remnants of a planet that never formed. Through 18 months of darkness and silence, its instruments quietly measuring the solar wind and cosmic rays, its cameras sleeping, conserving power and data capacity for the encounters ahead. And then Jupiter appeared. Section 3. The Giant Worlds. Voyager 2 reached Jupiter on July 9, 1979, 4 months after its twin had made its own historic flyby. By the time Voyager 2 arrived, the world had already seen Voyager 1's stunning photographs of Jupiter's banded atmosphere, the Great Red Spot, the volcanic surface of Io, the fractured ice shell of Europa. The first wave of astonishment had passed. The newspapers had moved on to other stories. Jupiter, having been revealed by Voyager 1, was now familiar. But Voyager 2 saw Jupiter differently. Not because its cameras were different, they were identical, but because its trajectory was different. Voyager 2 approached Jupiter from a different angle and at a different time, passing through the system on a path that took it closer to some moons and farther from others, revealing new faces of worlds that Voyager 1 had only glimpsed. The geometry of a planetary flyby determines everything. A spacecraft does not simply arrive at a planet and look around. It screams through the system at tens of thousands of miles per hour, spending only hours or days in the region where its cameras can resolve useful detail. The angle of approach determines which hemisphere of each moon is illuminated, which side of the planet faces the cameras, which features are visible and which are hidden in shadow. Voyager 1 and Voyager 2, arriving months apart on different trajectories, saw genuinely different Jupiters. Jupiter itself greeted Voyager 2 with atmosphere dynamics that had changed measurably in just 4 months. The cloud bands had shifted. The eddies and vortices that swirled at the boundaries between the jet streams had evolved, split, merged, and reformed. The Great Red Spot was still there, vast and patient, but the smaller storms around it had rearranged themselves. Jupiter's atmosphere, scientists realized, was not a static painting but a living, breathing, constantly changing system. Weather pattern of planetary scale that evolved on timescales of weeks and months, driven by the planet's furious 10-hour rotation and the enormous energy welling up from its deep interior. Voyager 2 made its closest approach to Jupiter on July 9th, passing within 404,000 miles of the cloud tops. That is farther than Voyager 1's closest approach, which had been 128,400 miles. But the different geometry gave Voyager 2 access to regions of the Jovian system that its twin had missed. The most significant difference was Europa. Voyager 1 had photographed Europa from a distance, capturing enough detail to reveal its smooth, cracked, icy surface, but not enough to study the cracks in detail. Voyager 2 passed closer to Europa and returned higher-resolution images that electrified the scientific community. The images showed a surface unlike anything in the solar system. Europa was covered in a global shell of water ice, extraordinarily smooth, with almost no impact craters visible. The absence of craters was itself a revelation. In the solar system, surfaces accumulate craters over time like a face accumulates wrinkles. Old surfaces are heavily cratered. Young surfaces are smooth. The near-total absence of craters on Europa meant that its surface was young, constantly being renewed by some process from below. Crossing that smooth ice was an intricate network of linear features, dark lines that stretched for hundreds and sometimes thousands of miles across the surface. Some were narrow and sharp, like cracks in a pane of glass. Others were broad and complex, with ridged edges and lighter central valleys, suggesting that material had welled up from below and frozen in the gap. The overall appearance was of an eggshell that had been cracked, and then healed, cracked and healed, again and again over millions of years. The implication was stunning. Beneath that ice there was almost certainly liquid water, an ocean, a global ocean of salt water, kept liquid by the same tidal heating that drove Io's volcanoes. Jupiter's gravity, pulling and flexing Europa with every orbit, generated enough friction in the Moon's interior to melt ice into water, maintaining a liquid ocean perhaps 60 miles deep beneath a frozen shell, perhaps 10 to 20 miles thick. A global ocean. On a moon 484 million miles from the Sun. Hidden beneath ice, warmed not by starlight but by the relentless kneading of gravity. Voyager 2's close-up images of Europa's fractured surface became some of the most studied photographs in planetary science. They launched a field of research that continues to this day. They inspired mission concepts, funding proposals, and decades of scientific debate about the possibility of life in Europa's dark ocean. And they planted a question in the minds of scientists that has never been answered. Is something alive down there, in the warm darkness beneath the ice, swimming in water that has never seen the sun? Io, the volcanic moon that had stunned the world during Voyager 1's flyby, greeted Voyager 2 with a show of its own. New eruptions had begun in the 4 months between the two encounters. Plumes that had been active during Voyager 1's visit had changed in size and intensity. Some had stopped entirely. New ones had appeared. The most dramatic change was at a volcanic feature called Pele, P-H-Le, one of the largest volcanic eruptions ever observed in the solar system. During Voyager 1's flyby, Pele had been ejecting a plume of sulfur dioxide roughly 200 miles above the surface. By the time Voyager 2 arrived, the plume had altered. The ring of sulfurous deposits around Pele's vent had expanded and changed color, like a bruise spreading and darkening on the skin of the moon. This was the first time anyone had directly observed volcanic change on another world, not inferred from geological evidence, not deduced from theory, directly observed in photographs taken 4 months apart, showing the same landscape in different states. Io was alive, actively, vigorously, continuously alive, a world in perpetual transformation, its surface being repainted in yellows and oranges and reds by the relentless volcanic activity driven by Jupiter's gravitational tides. Voyager 2 also made a critical discovery in Jupiter's ring system. Voyager 1 had detected a faint ring around Jupiter during its flyby, a surprise because Jupiter's rings are far too thin and dark to be seen from Earth with ground-based telescopes of that era. But Voyager 2, approaching from a different angle, was able to photograph the ring system in forward-scattered light, a viewing geometry where sunlight passes through the ring particles before reaching the camera. In this lighting, the tiny particles that make up Jupiter's rings scatter light forward very efficiently, like dust motes caught in a shaft of sunlight, and the ring system blazed into visibility. The images revealed a ring system far more complex than the single, faint ring that Voyager 1 had detected. There was a main ring, bright and relatively narrow. Inside it, a broader, fainter structure called the halo ring extended down toward Jupiter's cloud tops. And outside the main ring, 2 extremely faint gossamer rings stretched outward, fed by dust knocked off the small inner moons Amalthea, Am-O-The-E, and Thebe by micrometeorite impacts. Jupiter's rings are nothing like Saturn's magnificent system of ice and rock. They are made of microscopic dust grains, so tiny that they are continuously being swept away by Jupiter's powerful magnetic field and must be constantly replenished by impacts on the inner moons. They are ephemeral, transient, a perpetual dusting of debris that would vanish entirely if the source moons were removed. But they were there, and Voyager 2 photographed them in a way that Voyager 1 could not, simply because of the geometry of its approach. This is the beauty of sending 2 spacecraft instead of 1. Different trajectories mean different viewing angles, different lighting conditions, different sides of moons illuminated. What one spacecraft misses, the other may catch. The Voyager program was designed with this redundancy in mind, and at Jupiter, it paid off spectacularly. After Jupiter, Voyager 2 used the planet's gravity to redirect itself towards Saturn. The gravity assist, that elegant maneuver where a spacecraft steals a tiny fraction of a planet's orbital energy to boost its own speed, accelerated Voyager 2 and bent its trajectory outward. The spacecraft left Jupiter traveling faster than it had arrived, aimed at a point in space where Saturn would be roughly 2 years later. And then it fell silent again, its cameras sleeping, its instruments quietly measuring the solar wind and interstellar particles, coasting through the dark gulf between the 2 largest planets in our solar system. The distance between Jupiter and Saturn is roughly 456 million miles. Voyager 2 crossed it in about 2 years. During that crossing, there was nothing to see, nothing to photograph, nothing to aim the cameras at, just the emptiness. The slow, patient drift of a small machine through an ocean of nothing, guided by the trajectory it had been given and the laws of physics that govern all motion. And then, in August of 1981, Saturn appeared. Saturn was, if anything, more beautiful through Voyager 2's cameras than it had been through Voyager 1's. The viewing geometry was different. the ring tilt was different, the lighting was different, and the result was a collection of photographs that captured Saturn's rings with a clarity and a beauty that remains breathtaking to this day. Voyager 2's closest approach to Saturn occurred on August 26, 1981. The spacecraft passed within 63,713 miles of Saturn's cloud tops, significantly closer than Voyager 1's flyby distance of 77,260 miles. This closer approach gave Voyager 2 higher-resolution images of the ring system and access to regions of the system that Voyager 1 had not been able to study. The rings. Let us pause here and talk about the rings. Because Voyager 2's observations of Saturn's rings revealed a level of complexity that left scientists struggling for explanations. From Earth, Saturn's rings appear as a handful of broad, smooth bands separated by a few dark gaps. Through Voyager's cameras, those bands dissolved into thousands upon thousands of individual ringlets, each one a separate stream of icy particles orbiting Saturn at its own speed, separated from its neighbors by gaps that ranged from miles wide to barely detectable. The complexity was staggering. It was as if someone had taken the apparently simple structure visible from Earth and shattered it into 10,000 fine lines, each one with its own story, its own dynamics, its own explanation. Some of the structure was caused by gravitational resonances with Saturn's many moons. When a ring particle orbits Saturn at a period that is a simple fraction of the orbital period of a nearby moon, say exactly half or exactly one-third, the repeated gravitational tugs from the moon accumulate over time, nudging the particle out of that orbit and creating a gap. These are called resonance gaps, and they are among the most elegant examples of orbital mechanics in the solar system. The particles do not simply disappear. They are gently pushed into neighboring orbits, concentrating material on either side of the gap and creating a pattern that is both mathematically predictable and visually stunning. But much of the ring's fine structure was not so easily explained. There were features called density waves, spiral patterns triggered by the gravitational influence of moons and propagating through the ring like ripples on a pond. There were bending waves, vertical undulations in the ring plane, caused by moons orbiting slightly above or below the ring. There were spoke-like features, dark, radial markings that appeared and disappeared on the B-ring, rotating with the ring but seemingly defying the expected orbital mechanics. The spokes were eventually attributed to tiny dust grains levitated above the ring plane by electrostatic forces, charged by impacts from cosmic rays or by interactions with Saturn's magnetosphere. Each observation raised more questions than it answered. The rings, which had seemed so simple from Earth, turned out to be one of the most complex dynamical systems in the solar system. A laboratory of orbital mechanics, where billions of individual particles interact through gravity, collisions, and electromagnetic forces, producing patterns of exquisite beauty and maddening complexity. But the rings were not Voyager 2's most important observation at Saturn. That distinction belongs to a small, icy moon called Enceladus, N-S-L-U-Dus. Enceladus is one of Saturn's mid-sized moons, roughly 313 miles in diameter, about 1/7 the diameter of Earth's moon. Before Voyager, it was known to be bright, reflecting nearly 100% of the sunlight that hits it, making it the most reflective body in the solar system. But little else was known about it. Voyager 2 changed that. Its cameras revealed a surface that was strikingly varied. Parts of Enceladus were old and cratered, as expected for an icy moon in the outer solar system. But other regions were astonishingly smooth, with few or no craters visible. Long, parallel grooves and ridges cut across the surface, suggesting tectonic activity. In some areas, the terrain looked as if it had been resurfaced, the old craters buried beneath fresh material from below. The smooth, young terrain on Enceladus posed the same question that Europa had posed at Jupiter. Where was the heat coming from? Enceladus is small, far too small to retain internal heat from its formation. By the usual rules of planetary geology, it should have frozen solid billions of years ago. Yet here was evidence of geological activity, of resurfacing, of internal processes that were remaking the surface in defiance of the cold and the distance from the sun. The answer, as scientists later confirmed with the Cassini mission decades later, was the same as at Io and Europa: tidal heating. Saturn's gravity, combined with the gravitational influence of neighboring moons, flexes Enceladus just enough to melt ice in its interior and drive geological activity. Cassini would eventually discover that Enceladus harbors a global subsurface ocean beneath its icy shell, and that plumes of water vapor and ice particles erupt from fractures near its south pole, spraying material into space that forms Saturn's faint E ring. But the first hint, the first tantalizing suggestion that Enceladus was more than a frozen ball of ice, came from Voyager 2's photographs. Those images planted a seed that would germinate for 25 years, until Cassini arrived at Saturn and confirmed what Voyager had suggested: that another ocean world existed in the outer solar system, another place where liquid water and geological activity created conditions that might, possibly, support life. There is a moment in the Saturn encounter that deserves its own pause, a moment of decision, a moment that determined whether Voyager 2 would become the most far-traveled explorer in history, or simply another spacecraft that visited Jupiter and Saturn and then drifted into irrelevance. After Saturn, Voyager 2's trajectory could be adjusted. The gravity assist from Saturn would bend the spacecraft's path and accelerate it, but the exact flyby geometry determined where it went next. Two options were available. Option 1. Fly close to Triton, Saturn's largest moon, the mysterious world shrouded in orange haze. This was what Voyager 1 had done. A close Triton flyby would provide invaluable data about Triton's thick atmosphere and hidden surface. But it would bend Voyager 2's trajectory out of the plane of the solar system, ending any possibility of continuing to Uranus and Neptune. The grand tour would be over. Option 2. Skip Triton. Fly past Saturn on a trajectory that preserved the path to Uranus and Neptune. Sacrifice the Triton data in exchange for the chance to visit the two ice giants that no spacecraft had ever seen. Except that Triton's mysteries would have to wait for a future mission. This was not a difficult decision in hindsight. Voyager 1 had already flown past Triton and returned extensive data about its atmosphere. The most critical Triton science had already been done. The far greater scientific prize was the ice giants, worlds that no spacecraft had visited and that no funded mission would visit again for decades. Voyager 2 was the only chance, the only window, the only machine in position to make the journey, and so the decision was made. Voyager 2 would skip Triton. It would fly past Saturn on a trajectory optimized for the grand tour. It would continue to Uranus, and then, if it survived, to Neptune. The grand tour, the dream that had been officially denied, that had been reduced to an aspiration, that had been hidden inside the mission design like a secret hope, was about to become reality. Voyager 2 left Saturn in September of 1981, flung outward by the planet's gravity, aimed at a point in space where Uranus would be 4.5 years later. The spacecraft was now deep in the outer solar system, farther from the Sun than any active mission had ever been. The sunlight was dim, the temperatures were cold, the distances were vast, and ahead lay a world that existed, for all practical purposes, only as a point of light. But before we follow Voyager 2 to Uranus, let us take a breath. Let us settle into the quiet of this journey, because the crossing from Saturn to Uranus is one of the loneliest stretches of space that any machine has ever traversed. 4.5 years, nearly 1 billion miles, through a darkness so deep that the sun has shrunk to a bright star among many, through a silence so complete that the only sounds are the faint hum of electronics and the tick of a cosmic ray counter recording the passage of high-energy particles from distant supernovae. 4.5 years. Imagine it. From the fall of 1981 to the winter of 1986. On Earth, entire political administrations come and go in that time. Children are born and learn to walk and talk. Technologies emerge and become obsolete. The world changes in 1,000 visible and invisible ways. And throughout all of it, a small machine the size of a compact car drifts through the void at roughly 10 miles per second, carrying its cameras and instruments and golden record through the longest, loneliest leg of the longest journey any machine has ever taken. Let us follow it there now, to the 7th planet from the Sun, to the world that was discovered by accident, named after a god of the sky, and tilted so far on its side that it rolls through its orbit like a barrel. To Uranus, the first ice giant. Section 4. The Ice Giants. Uranus was discovered by accident. On March 13, 1781, a German-born musician and amateur astronomer named William Herschel was conducting a systematic survey of the night sky from his garden in Bath, England, using a telescope he had built himself. In the constellation Gemini, he noticed a faint object that did not look quite like a star. It had a visible disk where stars appeared as points, and over the following nights it moved against the background stars, confirming that it was not a star at all but something much closer. Something in our solar system. Herschel initially thought he had found a comet. It took months of observations by astronomers across Europe and careful mathematical analysis of its orbit to establish the truth. The object was not a comet. It was a planet. A new planet. The first planet discovered in recorded history that had not been known since antiquity. Mercury, Venus, Mars, Jupiter, and Saturn had been known for thousands of years, visible to the naked eye, tracked by civilizations from the Babylonians to the Greeks. But Uranus was too faint to see without a telescope. It had been there all along, circling the sun in the darkness beyond Saturn, invisible to every generation of humans, until Herschel pointed his homemade mirror at the sky and noticed something that did not belong. The discovery doubled the known size of the solar system overnight. Saturn, at roughly 9.5 astronomical units from the Sun, had been the boundary of the planetary system since the dawn of astronomy. Uranus, at roughly 19 astronomical units, pushed that boundary twice as far. Suddenly, the solar system was larger than anyone had imagined. And if there was one undiscovered planet hiding in the outer darkness, might there be others? The answer, of course, was yes. Neptune would be discovered 65 years later, in 1846. not by accident, but by mathematical prediction. But that is a story for later tonight. Uranus remained a mystery for over 2 centuries after its discovery. It was too far away, too faint, and too small in even the largest telescopes to reveal much detail. Astronomers could measure its size, roughly 4 times the diameter of Earth. They could determine its mass, roughly 14.5 times the mass of Earth. They could detect that it had an atmosphere, mostly hydrogen and helium with a significant amount of methane, the methane being responsible for the planet's distinctive pale blue-green color. And they knew one extraordinary thing about Uranus that set it apart from every other planet in the solar system. Uranus is tilted on its side. The planet's rotational axis is inclined 98 degrees from the perpendicular to its orbital plane. Where most planets spin like tops, with their poles pointing roughly up and down relative to their orbits, Uranus rolls along its orbit like a ball. Its poles turns pointing almost directly at the Sun. During Uranus's 84-year orbit, each pole experiences roughly 42 years of continuous sunlight, followed by 42 years of continuous darkness. No one knows with certainty why Uranus is tilted so dramatically. The leading theory is that early in the solar system's history, roughly 4 billion years ago, Uranus was struck by a massive protoplanet, an object perhaps the size of Earth. The collision was catastrophic enough to tip the entire planet over, shifting its rotational axis by nearly 90 degrees. The impactor was absorbed into Uranus, adding its mass to the planet and possibly contributing to the unusual distribution of heat in Uranus's interior. This is the violent origin of the quiet world that Voyager 2 was approaching. A world that had been knocked on its side by a cosmic collision billions of years ago, and had been rolling silently through the darkness ever since. Its extreme tilt-driving weather patterns, and seasonal cycles that have no parallel anywhere else in the solar system. Voyager 2 reached Uranus on January 24, 1986. The encounter occurred during one of the most difficult weeks in the history of the American space program. 4 days after Voyager 2's closest approach to Uranus, on January 28th, the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members. The Challenger disaster dominated the news for weeks. The extraordinary achievements of Voyager 2 at Uranus were largely overshadowed by the tragedy. This is one of the great ironies of the Voyager mission. The encounter with Uranus, the first and only close-up exploration of the 7th planet. The culmination of 8.5 years of flight through the outer solar system, occurred in the shadow of one of NASA's darkest hours. The scientists and engineers who had spent years preparing for this moment found their triumph muted by grief. The press conferences that should have celebrated Voyager's discoveries were held in an atmosphere of national mourning. And the public, reeling from the images of the shuttle disintegrating against a clear blue sky, had little attention to spare for a small machine photographing a distant world. But the science was extraordinary. Uranus, as seen by Voyager 2's cameras, was a surprise and a disappointment in equal measure. From a distance, the planet appeared as a nearly featureless blue-green sphere, its atmosphere so uniform in appearance that it looked almost bland. Unlike Jupiter, with its vivid bands and swirling storms, or Saturn, with its subtle banding and wind-driven jet streams, Uranus presented a face of almost eerie calm. A world of pale blue-green silence, as if the planet had smoothed away all its features and retreated behind a mask of methane haze. This apparent blandness concealed a complex reality. The methane in Uranus's upper atmosphere absorbs red light very efficiently, giving the planet its blue-green color. But this same methane forms a thick haze layer that obscures the deeper atmospheric features, hiding them beneath a veil that Voyager's cameras struggled to penetrate. When scientists applied heavy image processing to Voyager's photographs, enhancing the contrast and isolating specific wavelengths, faint cloud features emerged. Banded structures, subtle differences in albedo between the polar and equatorial regions, hints of atmospheric circulation driven by the planet's extreme axial tilt. But the real surprises were not in the atmosphere. They were in the magnetosphere, the rings, and above all, the moons. Uranus's magnetic field was one of the most unexpected discoveries of the encounter. On every planet previously studied, Jupiter, Saturn, and Earth, the magnetic field was roughly aligned with the rotational axis. The magnetic poles were within a few degrees of the geographic poles, which makes intuitive sense if the magnetic field is generated by convective motions deep in the planet's interior, motions that are influenced by the planet's rotation. Uranus broke this pattern completely. Voyager 2 discovered that Uranus's magnetic field is tilted approximately 59 degrees from the planet's rotational axis. Not a few degrees, not 10 or 20 degrees, 59 degrees. The magnetic poles are located closer to the equator than to the geographic poles, and the center of the magnetic field is offset from the center of the planet by roughly 1/3 of the planet's radius, as if the magnetic dynamo generating the field is not located at the core but in a shell of electrically conducting fluid much closer to the surface. This was baffling. No model of planetary magnetic fields predicted anything like this. The standard theory assumed that magnetic fields were generated deep in a planet's interior, where metallic hydrogen or other conducting fluids were set in motion by convective currents and shaped by the planet's rotation. A field tilted 59 degrees from the rotation axis suggested that something very different was happening inside Uranus. Perhaps the conducting region was a thin shell of water and ammonia, compressed into an electrically conducting state at intermediate depths, rather than the metallic hydrogen core found in Jupiter and Saturn. Perhaps the planet's extreme tilt and unusual internal structure created conditions for a dynamo that operated by different rules. Scientists are still debating the explanation. The Uranian magnetic field remains one of the outstanding puzzles of planetary science, a clue to the planet's internal structure that has not yet been fully decoded. Voyager 2 discovered 10 new moons of Uranus, all of them small, dark, and orbiting close to the planet. Before Voyager, only 5 moons were known: Miranda, Ariel, Aireel, Umbriel, Briel, Titania, Titania, and Oberon, all named after characters from the works of William Shakespeare and Alexander Pope. Voyager's discovery of 10 additional moons more than tripled the known satellite count overnight. But the most remarkable moon was one that was already known. The smallest and innermost of the 5 classical moons. A tiny world only 293 miles in diameter, barely 1/7 the diameter of Earth's moon. A world that, by every reasonable expectation, should have been a dead, cratered ball of ice. Its name was Miranda, and what Voyager 2 found there was one of the most visually bizarre and geologically confusing sights in the entire solar system. Miranda's surface is a patchwork of wildly different terrains, jumbled together as if the moon had been assembled from spare parts of several different worlds. There are old, heavily cratered regions that look exactly like what you would expect on a small, ancient moon. Surfaces pounded by billions of years of impacts, frozen and dead and unchanged since the early days of the solar system. But interspersed with these ancient cratered plains are three enormous, roughly rectangular regions of intensely deformed terrain that scientists call corona, Ku-ro-ni. These corona are unlike anything else in the solar system. They contain parallel ridges and grooves, concentric patterns of light and dark material, and cliffs of staggering height. The most dramatic feature on Miranda is a cliff called Verona Rupes, Vu-ro-h-nu-ro-o-pes, which towers approximately 12 miles above the surrounding terrain. 12 miles, on a world only 293 miles across. If you could stand at the edge of Verona Rupes and drop a stone, it would take roughly 10 minutes to reach the bottom, falling slowly in Miranda's feeble gravity, 1/79th of Earth's. It is one of the tallest known cliffs in the solar system, proportionally as dramatic as a cliff 60 miles high would be on Earth. The question that Miranda poses is simple. How? How did a tiny moon, far too small to generate its own internal heat, produce terrain this complex and this violent? How did a world that should be dead produce cliffs 12 miles high and regions of terrain that look like they were squeezed through a machine? Several theories have been proposed. One early idea, now largely abandoned, suggested that Miranda was shattered by a catastrophic impact and then reassembled by gravity, with the different terrain types representing pieces that came back together in a jumbled arrangement. A more current theory invokes tidal heating, similar to what drives Io's volcanism and Europa's ocean. Miranda may have been locked in an orbital resonance with one of the larger Uranian moons at some point in its past, causing tidal flexing that heated its interior enough to drive geological activity. When the resonance broke, the heating stopped and the surface froze in place, preserving a record of the brief, violent episode when tidal forces kneaded this tiny world like dough. Whatever the explanation, Miranda is a reminder that the outer solar system is full of surprises. Small does not mean simple. Cold does not mean dead. And a world the size of a large city can harbor landscapes that dwarf anything on Earth. The three coronae on Miranda each have their own distinct character and their own name. Arden Corona, Elsinore Corona, and Inverness Corona, all named after settings in Shakespeare's plays, because the Uranian moons carry the legacy of the playwright in their geography as well as their names. Arden Corona, the oldest of the three, has a relatively subdued appearance, its ridges and grooves softened by time and cratering. Elsinore Corona, named after the castle in Hamlet, is more complex, with concentric ridges that spiral inward like the grooves of a fingerprint. And Inverness Corona, named after the setting of Macbeth, is the most dramatic, with sharp, angular ridges and deep troughs that cut into the surrounding terrain like knife wounds. The juxtaposition of these corona with the ancient, cratered plains creates one of the most jarring visual contrasts on any world in the solar system. It is as if two completely different geological histories had been pasted together on the same small sphere, old and new, dead and active, smooth and violent, side by side with no gradual transition between them. The boundary between a corona and the surrounding cratered terrain is sharp and abrupt, like a line drawn on the surface, separating two worlds that should not exist on the same body. Voyager 2's cameras captured Miranda for only a few hours. The spacecraft was moving so fast that the encounter was brief, the images limited to a single hemisphere. The far side of Miranda has never been photographed. We have seen only half of this bizarre little world, and what we have seen raises more questions than it answers. Miranda is a puzzle with half the pieces missing, a mystery that Voyager 2 opened but could not solve. And no mission currently planned will return to solve it. Let that settle for a moment. Half a world photographed once, 39 years ago, by a spacecraft that was already 9 years old and running on slowly dying nuclear batteries. That is all we have. That is all we may have for decades to come. And yet those few photographs have been studied, debated, modeled, and argued over by planetary scientists for nearly 4 decades, because what they show is so strange, so unexpected, so difficult to explain, that they challenge our fundamental understanding of how small worlds work. Voyager 2 also studied Uranus's ring system. The rings of Uranus had been discovered only 9 years before the encounter, in 1977, when astronomers observing a stellar occultation, the passage of Uranus in front of a distant star, noticed that the star's light dimmed briefly several times before and after. The planet blocked it. The symmetric pattern of dimming on both sides indicated narrow rings encircling the planet. Voyager 2 confirmed and expanded on these ground-based observations. The cameras revealed a system of thin, dark rings, strikingly different from Saturn's bright, broad rings. Uranus's rings are narrow and widely spaced, with broad, dark gaps between them. They are composed of very dark particles, reflecting only about 5% of the sunlight that hits them, which is why they had remained undetected for so long. The ring particles are thought to be primarily water ice mixed with some dark organic material, rendered nearly black by billions of years of bombardment by cosmic radiation. The outermost and brightest ring, called the epsilon ring, is peculiar in several ways. It varies in width around its circumference, from as narrow as 12 miles to as wide as 60 miles, and it also varies in brightness, being denser where it is narrower and sparser where it is wider. This behavior is governed by 2 small shepherd moons, Cordelia, Cordelia, and Ophelia, that orbit just inside and outside the ring. Their gravitational influence confines the ring particles, preventing them from spreading out. Without these shepherds, the epsilon ring would dissipate within a few thousand years, spreading its material into a diffuse cloud. Voyager discovered 2 of Uranus's rings that had not been detected from Earth, bringing the total to 11. The ring system, while far less visually dramatic than Saturn's, provided valuable insights into the physics of ring dynamics and the interplay between rings and moons. The Uranus encounter lasted approximately 6 hours, from the time the spacecraft entered the useful imaging range to the time it exited, having crossed the system at a speed of roughly 45,000 miles per hour. In those 6 hours, Voyager 2 accomplished more science at Uranus than all of the ground-based telescopes that had studied the planet since William Herschel discovered it 205 years earlier. And then it was gone. Uranus's gravity, the same force that had revealed the planet's tilted magnetic field and held its battered moons and dark rings in place, bent Voyager 2's trajectory and flung it onward, toward the outermost giant planet, toward the world that had been predicted on paper before it was ever seen through a telescope, toward a blue jewel of ice and wind that orbited in darkness so deep that noon on its surface was dimmer than twilight on Earth, toward Neptune. The crossing from Uranus to Neptune would take 3.5 years, nearly 1 billion additional miles, through a cold so profound that the very concept of temperature began to lose its everyday meaning. From the fall of 1986 to the summer of 1989, Voyager 2 coasted through the void, carrying a cargo of data from Uranus and a hope that its aging systems would hold together long enough for one more encounter. Let us follow it there, to the last world. Section 5. The Last World. Neptune was discovered not by looking through a telescope, but by looking at equations on a piece of paper. In the decades after Uranus was discovered, astronomers noticed something troubling. Uranus was not following the orbit that Newton's laws predicted. It was being pulled slightly off course by something massive, something invisible, something beyond the known boundary of the solar system. In 1845 and 1846, two mathematicians working independently reached the same conclusion. The Frenchman Urbain Le Verrier, Urbain Le Verrier, and the Englishman John Couch Adams each calculated the position of the unknown planet that was perturbing Uranus's orbit. Le Verrier sent his prediction to the Berlin Observatory, where the astronomer Johann Galle pointed his telescope at the predicted location on September 23, 1846, and found Neptune within 1 degree of where Verrier said it would be. It was one of the great triumphs of mathematical physics. A planet discovered not by observation but by prediction. Not by seeing it, but by calculating where it must be, based on its gravitational influence on something millions of miles away. Newton's laws, written 159 years earlier, had reached across the solar system and revealed a hidden world. Neptune is the 8th and outermost planet of our solar system. It orbits the Sun at an average distance of roughly 30 astronomical units, about 2.8 billion miles, taking 164.8 years to complete a single orbit. Since its discovery in 1846, it has completed only one full orbit, passing through its discovery point for the first time in July of 2011. If you are hearing this, Neptune is still in what might be called its first known year. Neptune is slightly smaller than Uranus, but significantly more massive. Its diameter is roughly 30,500 miles, about 3.8 times the diameter of Earth. Its mass is 17.15 times the mass of Earth, compared to Uranus's 14.54. This means Neptune is denser than Uranus, its interior packed more tightly, its gravity stronger at the cloud tops. The two planets are often grouped together as ice giants, distinguished from the gas giants Jupiter and Saturn by their smaller size and their composition, which is dominated not by hydrogen and helium, but by heavier substances, water, ammonia, and methane, compressed into exotic states by the tremendous pressures deep inside the planet. From Earth, Neptune appears as a faint blue dot, barely visible through a large backyard telescope, its surface utterly featureless at that distance. The finest ground-based telescopes of the 1980s could resolve it as a small disk, but no details were visible. Everything we knew about Neptune before Voyager 2 arrived was inferred from indirect measurements: the planet's mass from its gravitational effects, its composition from its spectrum, its temperature from its infrared emissions. And then Voyager 2 arrived, and Neptune became a world. Voyager 2 reached Neptune on August 25, 1989. It had been traveling for 12 years, 12 years since the warm Florida morning when it climbed into the sky. 12 years since the stuck receiver and the bulky scan platform and the nervous engineers who wondered if this machine would survive its first planetary encounter, let alone its last. The approach to Neptune was one of the most technically challenging operations in the history of space exploration. At Neptune's distance, the sunlight was roughly 900 times fainter than at Earth. Voyager 2's cameras, designed to photograph the brightly lit surfaces of Jupiter and Saturn, had to capture images in near darkness. To compensate, the exposure times had to be lengthened dramatically. But longer exposures mean motion blur, because the spacecraft is moving at high speed relative to its target. The solution was a technique called image motion compensation. The entire spacecraft was slowly rotated during each exposure, turning at exactly the rate needed to keep the target stationary in the camera's field of view. This required extraordinary precision in the spacecraft's attitude control system, pointing the camera with an accuracy measured in thousandths of a degree, while the spacecraft rotated, all controlled by a computer with 69 kilobytes of memory from a distance of nearly 3 billion miles. The software that made this possible did not exist when Voyager 2 launched. It was written and uploaded years later, after the spacecraft was already billions of miles from Earth. Engineers at the Jet Propulsion Laboratory developed new compression algorithms to squeeze more data through Voyager's painfully slow radio link. They reprogrammed the spacecraft's computers to execute maneuvers that had never been planned or tested during development. They turned a spacecraft designed for the relatively bright environments of Jupiter and Saturn into one capable of operating in the dim twilight of Neptune. This is one of the most underappreciated aspects of the Voyager mission. The spacecraft that arrived at Neptune in 1989 was not the same spacecraft that launched in 1977. Its hardware was identical, yes, every circuit and sensor and motor the same as it had been at launch. But its software, its capabilities, its repertoire of operations had been completely transformed. Voyager 2 had evolved, not through physical modification but through the ingenuity of the humans who guided it, who continued to teach an old machine new tricks, even as it sailed farther and farther from home. Neptune, as revealed by Voyager 2's cameras, was stunning. Where Uranus had presented a bland, nearly featureless face, Neptune was vivid and dynamic. A deep, luminous blue, more intense and more beautiful than Uranus's pale blue-green. Neptune's atmosphere was alive with weather. The color comes from methane in the upper atmosphere, as with Uranus. Methane absorbs red light, leaving the reflected sunlight shifted toward the blue end of the spectrum. But Neptune's blue is deeper and richer than Uranus's, and the reasons for the difference are still debated. Neptune's atmosphere may contain a different distribution of haze particles, or the methane may be present at different altitudes, or there may be an additional absorber in Uranus's atmosphere that is absent in Neptune's. The exact cause of the color difference remains one of the open questions of planetary science. But it was not the color that shocked the scientists. It was the weather. Voyager 2 discovered a massive storm in Neptune's southern hemisphere that scientists named the Great Dark Spot. It was an anticyclonic storm, roughly the size of Earth, dark against the surrounding blue atmosphere, with wispy white clouds of methane ice hovering at its edges like cirrus clouds at the edge of a hurricane. The resemblance to Jupiter's Great Red Spot was immediately obvious, and scientists initially wondered whether the Great Dark Spot was a similar long-lived feature. a permanent fixture of Neptune's atmosphere. But there was a crucial difference. The great red spot of Jupiter has been observed for at least 350 years and is probably much older. The great dark spot of Neptune, when the Hubble Space Telescope observed Neptune in 1994, just 5 years after Voyager's flyby, was gone, vanished, replaced by a new dark spot in the northern hemisphere that itself would later disappear. Neptune's storms, unlike Jupiter's, are transient. They form, grow, rage for a few years, and then dissolve, replaced by new storms in new locations. Neptune's atmosphere is a constant cycle of creation and destruction, a weather system of planetary scale that remakes itself every few years. And the winds. The winds on Neptune are the fastest in the solar system. Voyager 2 measured wind speeds exceeding 1,200 miles per hour at some latitudes. 1,200 miles per hour. Faster than the speed of sound at sea level on Earth. Faster than any wind on Jupiter or Saturn. Faster than anything that should be possible on a world so far from the Sun, where the energy input from sunlight is 1,000th of what Earth receives. This is one of Neptune's great paradoxes. The planet receives almost no heat from the Sun. At 30 astronomical units, the sunlight reaching Neptune is less than 1/9 of 1% of the intensity at Earth. And yet Neptune's atmosphere is more dynamic, more turbulent, and more violent than the atmospheres of planets much closer to the Sun. Where does the energy come from? The answer lies deep inside Neptune. The planet radiates more than twice as much heat as it receives from the Sun. This internal heat, left over from Neptune's formation and sustained by ongoing gravitational contraction and differentiation in the interior, drives the atmospheric circulation. Neptune is essentially heated from within, like a pot on a stove, and that internal heating generates the powerful convective currents that drive the winds to supersonic speeds. The Sun contributes almost nothing. Neptune is, in a very real sense, a weather system powered by its own interior, independent of the star it orbits. Think about that for a moment. On Earth, all weather is driven by the Sun. The Sun heats the tropics more than the poles, creating temperature gradients that drive the global circulation of the atmosphere. Without the Sun, Earth's weather would cease. The winds would die. The storms would dissipate. The atmosphere would settle into a cold, motionless equilibrium. Neptune's weather does not care about the Sun. It is powered from below, by heat leaking out of the planet's interior, heat that has been trapped there since Neptune formed 4.5 billion years ago. That internal heat drives a convective upwelling, rising columns of warm gas that punch through the upper atmosphere and create the visible cloud features that Voyager photographed. The wind speeds are a consequence of this vigorous internal circulation, amplified by Neptune's rapid rotation, a period of roughly 16 hours, which stretches and shears the atmospheric currents into the banded jet stream patterns that drive the supersonic winds. It is a kind of weather that we have no experience with on Earth. A weather system that would continue to operate even if the Sun went dark. A world that carries its own energy source, its own engine, its own reason for turbulence and motion and change, buried deep inside where no camera or instrument can reach. Neptune is a planet that makes its own weather from the heat of its own birth, and will continue doing so for billions of years to come. But the most extraordinary discovery at Neptune was not the planet itself. It was the largest of Neptune's moons, a world called Triton, Triton. Triton is a world that should not be where it is. Everything about it is wrong, in the most scientifically fascinating way. Triton orbits Neptune in the wrong direction. While virtually every large moon in the solar system orbits its parent planet in the same direction that the planet rotates, a prograde orbit, Triton orbits Neptune in the opposite direction. This is called a retrograde orbit, and for a moon as large as Triton, 1,700 miles in diameter, roughly 80% the size of Earth's moon, it is essentially impossible for it to have formed in place. Moons that form from the same disk of gas and dust as their parent planet inherit the planet's rotation direction. The only explanation for Triton's retrograde orbit is that it did not form around Neptune at all. Triton was captured. The capture hypothesis holds that Triton originally formed in the Kuiper Belt, the vast ring of icy bodies that extends beyond Neptune's orbit from roughly 30 to 50 astronomical units from the Sun. The Kuiper Belt is home to thousands of known objects and probably millions more, remnants of the solar system's formation that were too far from the Sun and too thinly spread to coalesce into a planet. Pluto, once considered the ninth planet, is now recognized as one of the largest Kuiper Belt objects. Triton, in this scenario, was a large Kuiper Belt object, perhaps similar in size and composition to Pluto, that was wandering through the outer solar system when it passed too close to Neptune. Neptune's gravity captured it, pulling it into orbit. The capture process would have been violent and chaotic, placing Triton initially in a highly elliptical orbit that gradually circularized over hundreds of millions of years through tidal interactions with Neptune. That circularization process would have generated enormous amounts of heat in Triton's interior, enough to melt the moon entirely, resurfacing it and driving geological activity that may have persisted for billions of years. The capture of Triton would have been catastrophic for any moons that already existed around Neptune. A large body entering the system on a retrograde orbit would have disrupted the orbits of any pre-existing regular moons, potentially causing collisions and ejections that destroyed Neptune's original satellite system. Triton is essentially an invader, a foreign body that crashed into Neptune's family, destroyed the existing members, and took their place. The small, irregular moons that orbit Neptune today, the tiny ones discovered by Voyager 2 and subsequent observations, are thought to be debris from the destruction of the original satellite system, or objects captured later from the surrounding Kuiper Belt. Voyager 2 flew past Triton on August 25, 1989, passing within roughly 25,000 miles of the surface. What it found was a world of haunting, alien beauty. Triton's surface temperature is roughly minus 235 degrees Celsius, or minus 391 degrees Fahrenheit. It is one of the coldest measured surfaces in the solar system. At those temperatures, nitrogen freezes solid, and the surface of Triton is coated in a layer of nitrogen ice that reflects sunlight with surprising efficiency, giving the moon a bright, pinkish hue. The terrain was unlike anything Voyager had encountered before. Much of the surface was covered in a bizarre landscape that scientists named cantaloupe terrain, because it resembled the skin of a cantaloupe melon. A network of dimples and ridges, roughly circular depressions separated by raised rims, covering vast areas of the surface. The origin of the cantaloupe terrain is still debated. It may be the result of diapirism, Dy-U-Pirism, a geological process where warmer, less dense material rises through colder, denser material from below, like blobs in a lava lamp, deforming the surface as it rises. Or it may be the result of some other process unique to Triton's exotic ice composition. No one knows for certain, but the most astonishing discovery was the geysers. As Voyager 2 flew over Triton's south polar region, its cameras captured dark streaks on the surface, elongated marks stretching across the bright nitrogen ice for dozens of miles. These streaks all pointed in the same general direction, trailing downwind, and they emanated from specific points on the surface. Scientists interpreted these features as the aftermath of geyser-like eruptions. Nitrogen gas, heated by the faint sunlight that penetrates Triton's thin atmosphere and is absorbed by dark material just beneath the translucent surface ice, builds up pressure under the ice cap, until it bursts through in a violent plume, carrying dark material with it. The plume rises several miles into Triton's thin nitrogen atmosphere, and is then carried by prevailing winds, depositing the dark material in long, streaking trails across the bright ice. Active geysers, on a world 2.8 billion miles from the Sun, where the temperature is 40 degrees above absolute zero, where the surface is frozen nitrogen and the atmosphere is barely there, a thin veil of nitrogen gas so tenuous that it would register as a hard vacuum by terrestrial standards. The discovery of geological activity on Triton at those extreme temperatures expanded the envelope of what scientists considered possible. Before Triton, geological activity was associated with heat, internal heat, tidal heat, solar heat. Triton demonstrated that even a minimal energy source, in this case the feeble sunlight reaching 30 astronomical units, could drive geological processes on a world of exotic ices at temperatures that would freeze carbon dioxide solid. The solar system, it seemed, was even more creative than anyone had imagined. The encounter with Triton was the last act of Voyager 2's planetary mission. After 12 years and 4 giant planets, there were no more worlds to visit. Neptune's gravity bent Voyager 2's trajectory sharply downward, below the plane of the solar system, aimed toward the constellation Sagittarius and the galactic center beyond. The spacecraft left the planetary system heading in a direction that would never again bring it close to a known planet. As Voyager 2 receded from Neptune, its cameras looked back and captured a final crescent image of the blue planet and its captured moon, thin crescents of pale light against the blackness of space. It was a farewell photograph, a goodbye, the last close-up image of a planet that Voyager 2 would ever take, the last close-up image of Neptune that any spacecraft has taken. To this day, more than 36 years later, no spacecraft has returned to Neptune. Think about that. Every photograph of Neptune that exists in close-up detail, every image that shows the great dark spot, the wispy methane clouds, the rings, the dark geysers of Triton, every one of those photographs was taken by a single spacecraft during a single flyby, in a window of time lasting roughly 12 hours, in August of 1989. One machine, one pass, one chance, and then it was over. There is a particular kind of loneliness in that fact. Not for Voyager, which feels nothing, but for us. We have seen Neptune only once. We have visited Triton only once. We have measured the winds and the magnetic field and the temperature and the composition of the last giant world in our solar system, and then we turned away and did not go back. As of today, there is no approved mission to return to Neptune or Uranus. There are proposals, there are concepts, there are scientists who have dedicated their careers to advocating for an ice giant mission. A decadal survey of planetary science has identified a Uranus orbiter as a high-priority mission for the coming decades. But the funding has not materialized. The mission has not been approved. The rocket has not been built. And the planetary alignment that would allow a Jupiter gravity assist to speed the journey to the ice giants will not be favorable again until the 2030s and beyond. This means that everything we know about Uranus and Neptune in close-up detail comes from a single spacecraft that was designed in the 1970s, built with technology less powerful than a modern smartwatch, and powered by a few pounds of slowly decaying plutonium. Everything, every data point, every photograph, every measurement. Voyager 2 is the sole source. Let that settle over you for a moment. Imagine a species that builds a machine, sends it on a 12-year journey across 3 billion miles of space, uses it to explore two worlds that no other machine has ever visited, and then does not go back for half a century and counting. It is a strange mixture of ambition and neglect, of daring and forgetfulness. We crossed an ocean, and then we forgot how to build ships. But the data remains. The photographs remain. The measurements remain. And they have shaped everything we understand about the ice giants, about the outer solar system, about the diversity of worlds that orbit our sun. Voyager 2's fleeting visits to Uranus and Neptune are the foundation on which all future ice giant missions will be built. When humanity finally returns, and it will return, every mission planner and every instrument designer will begin by studying what Voyager 2 found, guided by the ghost of a machine that passed through those systems decades ago and saw them for the first time with human-built eyes. And now, with the planetary encounters behind it, Voyager 2 faced the same fate as its twin: the long, slow, silent journey outward, through the heliosphere, toward the heliopause, toward the boundary where the sun's breath gives way to the wind between the stars. Let us follow it there. One last time. Section 6. 2 bottles in the ocean. After Neptune, Voyager 2 flew south, where its twin, Voyager 1, had been deflected upward and northward by its Titan flyby at Saturn, heading toward the constellation Ophiuchus, off Iaucus. Voyager 2's Neptune flyby sent it downward, below the plane of the solar system, heading toward the constellation Sagittarius, Sagittarius. The 2 twins, born in the same room, launched from the same place, carrying identical golden records, were now diverging, heading in different directions through the galaxy, each one alone, each one carrying the same message. 2 bottles thrown into the same ocean, caught by different currents, sailing toward different shores that may not exist. For the next 29 years, Voyager 2 coasted through the heliosphere. Its cameras had been turned off. Its most power-hungry instruments had been shut down. The spacecraft ran in a kind of minimal survival mode, keeping only the most essential, particle and field instruments active, measuring the solar wind, counting cosmic rays, mapping the sun's magnetic field as it stretched thinner and thinner with distance. The data was not dramatic. There were no photographs to splash across magazine covers, no vivid images of storms or volcanoes or fractured ice. Just numbers. Streams of numbers, transmitted at 160 bits per second, traveling at the speed of light across the growing void, arriving at Earth as signals so faint that they had to be extracted from the cosmic background noise by the most sensitive radio receivers on the planet. But those numbers told a story. The same story that Voyager 1's numbers had told 6 years earlier. a story of a boundary approaching, a place where the sun's influence ends and the galaxy begins. On November 5, 2018, Voyager 2 crossed the heliopause and entered interstellar space. It became the second human-made object to do so, 6 years after its twin had made the same crossing. The heliopause, as we discussed when following Voyager 1's journey, is the boundary where the outward-flowing solar wind, that river of charged particles from the sun, is finally balanced and then overwhelmed by the pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. Inside the heliopause, you are in the sun's domain. Outside it, you are in the galaxy. But Voyager 2's crossing of the heliopause was scientifically even more valuable than Voyager 1's, and the reason is a single instrument. When Voyager 1 crossed the heliopause in 2012, one of its key instruments, the Plasma Science Experiment, or PLS, had been non-functional since 1980. The instrument had broken more than 3 decades earlier, and without it, Voyager 1 could not directly measure the density and temperature of the plasma around it. Scientists had to infer the plasma conditions from indirect measurements using the spacecraft's plasma wave instrument to detect oscillations in the plasma and calculate its density from those oscillations. Voyager 2's plasma science instrument, by contrast, was still working. It had been operational for the entire mission, more than 40 years, and it was still functioning when the spacecraft crossed the heliopause in 2018. This meant that Voyager 2 could directly measure the plasma on both sides of the boundary. The hot, tenuous solar wind on the inside, and the cool, denser interstellar plasma on the outside. The data was extraordinary. As Voyager 2 crossed the heliopause, the PLS instrument recorded a sharp, dramatic transition. The density of the plasma jumped by a factor of roughly 20 over a very short distance. The temperature dropped. The composition changed. The flow speed and direction shifted. In the space of a few hours, as measured by the rate at which the spacecraft was moving through the boundary region, Voyager 2 passed from one ocean into another, and what it found on the other side was different from what Voyager 1 had found. The interstellar medium is not uniform. The heliopause is not a smooth, symmetrical sphere. Voyager 1 crossed the heliopause on the nose of the heliosphere, the side facing into the interstellar wind, at a distance of about 122 astronomical units from the Sun. Voyager 2 crossed on a flank, heading in a different direction at a distance of about 119 astronomical units. The boundary was closer to the Sun on Voyager 2's side, suggesting that the heliosphere is not perfectly spherical but slightly compressed and asymmetric, shaped by the interstellar wind that flows past it like water flowing past a rock in a stream. The plasma conditions at the boundary were also different. The transition observed by Voyager 2 was sharper and more abrupt than what Voyager 1 had measured. There was evidence of a thin boundary layer, a skin on the heliosphere, that had not been detected at Voyager 1's crossing point. And the interstellar magnetic field on Voyager 2's side had a slightly different orientation and strength than on Voyager 1's side, consistent with the expectation that the local interstellar medium is not perfectly uniform, but varies in direction and intensity across the vast distances separating the two crossing points. 2 spacecraft, 2 crossing points, 2 different views of the same boundary. Together, the twin crossings provided the first 3-dimensional picture of the heliosphere's edge, allowing scientists to begin mapping the shape and structure of the bubble that surrounds our solar system. It was the kind of science that could only be done with two independent probes, separated by billions of miles and years of travel, each measuring the same boundary from a different vantage point. This is the legacy that people often overlook when they think about the Voyager mission. The planetary encounters get the attention. The photographs of Jupiter's storms and Saturn's rings and Neptune's blue atmosphere are the images that people remember. But the heliopause crossings, quiet and unspectacular as they were, may be the most scientifically important measurements that either spacecraft ever made, because they revealed the shape of our home, not our planetary home, not Earth, but our stellar home, the heliosphere, the bubble of solar wind that shelters the entire solar system from the full force of the interstellar medium, the membrane between inside and outside, the skin of the sun's domain. And now, both Voyagers are out there, both in interstellar space, both moving away from the sun, from each other, from everything they have ever known. Two small machines in an ocean of darkness, each carrying an identical golden record, each sailing toward a different part of the galaxy. Let us trace their paths forward, gently, the way you might trace two lines on a map with your fingertip, watching them diverge. Voyager 1 is heading north and slightly eastward, relative to the galactic plane, toward the constellation Ophiuchus. It is traveling at roughly 17.1 kilometers per second. In about 40,000 years, it will pass within 1.6 light-years of a red dwarf star called Gliese 445 in the constellation Camelopardalis. Voyager 2 is heading south, below the plane of the ecliptic, toward the constellation Sagittarius. It is traveling at roughly 15.3 kilometers per second, somewhat slower than its twin, because Neptune's gravity assist was less efficient than the one Voyager 1 received at Jupiter and Saturn. In about 40,000 years, Voyager 2 will pass within 1.7 light-years of a star called Ross 248, a small red dwarf in the constellation Andromeda. Two different stars, two different directions, two different futures. The twins that were born together, that were built side by side in the same room, that launched from the same pad 16 days apart, are now separated by billions of miles and heading in directions that diverge more with every passing year. They will never meet again. They will never be in the same part of the galaxy again. They are, from this point forward, solitary travelers, each one alone in the most complete and permanent sense of the word. And what will become of them? What will happen to these two small machines over the vast spans of time that lie ahead? In roughly 10 years, give or take, the last instruments on both spacecraft will be shut down as the power from the decaying plutonium drops below usable levels. The transmitters will fall silent. The last signals, faint whispers traveling at the speed of light across billions of miles, will arrive at Earth's radio dishes and then stop. Mission Control will note the time, and the communication link that has been maintained for nearly 6 decades will be severed. The two most distant objects ever created by human hands will go deaf and mute forever. But they will not stop moving. There is nothing in interstellar space to slow them down. No air, no friction, no resistance. The only forces acting on them are the gravity of the sun, growing weaker with every passing year, and the gravitational influence of the galaxy itself, a vast, gentle pull that will slowly curve their trajectories over hundreds of thousands of years. In 1,000 years, each spacecraft will have traveled roughly 10 billion additional miles. still within the Oort cloud, still technically within the Sun's gravitational domain, but so far from anything recognizable that the concept of home will have lost all meaning. In 10,000 years, they will be deep in the Oort cloud, that vast spherical halo of trillions of icy bodies that extends roughly 100,000 astronomical units from the Sun. The chance of either spacecraft hitting an Oort cloud object is essentially zero. The Oort cloud is so vast and so sparsely populated that a spacecraft could fly through it for 1,000,000 years without encountering anything larger than a grain of sand. In 100,000 years, both spacecraft will have left the Oort cloud behind. They will be truly free, free of the Sun's gravity, free of the solar system, adrift in interstellar space, following their own orbits around the center of the galaxy, independent of the star that warmed the world where they were built. In 1,000,000 years, Voyager 1 will have traveled roughly 56,700 light-years. Voyager 2, traveling slightly slower, will have traveled roughly 50,000 light-years. Both will be in completely different parts of the galaxy. The star patterns in their skies, if they had skies, would be unrecognizable. The Sun would be invisible. The solar system would be a memory held in no mind, recorded in no data, preserved in nothing except the faint traces of human civilization that might or might not still exist on a planet that might or might not still be habitable. But the spacecraft will endure. Aluminum does not corrode in a vacuum. Titanium does not weaken without moisture. Gold does not tarnish without an atmosphere. The interstellar medium will slowly sandblast their surfaces, pitting the metal with microscopic craters from dust grain impacts over hundreds of thousands of years. The thermal blankets will eventually crack and flake away, degraded by cosmic radiation. The electronics will be long dead, the silicon chips damaged beyond repair by decades of cosmic ray bombardment. But the structures will survive. The antenna dishes, the instrument booms, the central bus, scarred and worn and stripped of their insulation but intact. Recognizable, clearly artificial, and on each one, mounted on a bracket, protected by a metal cover, a golden record will remain, slightly pitted by 1,000,000 years, of micrometeorite impacts, but readable, the grooves intact, the information preserved, 2 identical records, 2 identical messages, carrying the same music, the same greetings, the same photographs, the same sounds of wind and rain and laughter and wails, carrying the brainwaves of the same woman in love, sailing through different parts of the galaxy, separated by thousands of light-years, each one a redundant copy of the other. As if the people who made them understood, consciously or not, that sending one message is a hope, but sending 2 is an act of determination. There is something profoundly moving about the idea of 2 identical messages, launched from the same place at almost the same time, diverging through the galaxy for millions of years, each one carrying the same portrait of the same species on the same planet. It is as if we put the same letter in 2 bottles and threw them into the ocean from opposite sides of the same beach. Each bottle carries the same words, the same hope, the same quiet assertion that we existed and that we mattered. And each bottle sails away in a different direction, doubling the already infinitesimal chance that someone, somewhere, might find one of them. The golden records on Voyager 1 and Voyager 2 are identical. The same 115 images, the same 55 greetings, the same 27 musical selections, the same sounds of Earth, the same Anne Druyan brainwaves, the same pulsar map pointing back to the sun, the same instructions for playing the record, engraved on the cover in a language of physics and mathematics that any sufficiently intelligent finder should be able to decipher. But the two records will have different journeys, different encounters with starlight and cosmic dust, different gravitational tugs from different passing stars, different erosion patterns on their surfaces. After 1,000,000 years, the two records will be subtly different, worn in different ways by different environments, like two copies of the same book left in different climates, one in a desert and one by the sea. The words will be the same, but the patina will tell different stories, and perhaps that is fitting. Because the message on the golden record is itself a kind of snapshot, a frozen moment in the history of a species that never stops changing. The Earth of 1977, the year the records were pressed and launched, is already a different world from the Earth of today. The languages have evolved. The music has changed. Some of the speakers whose voices are on the record are dead. Some of the places photographed no longer look the same. The golden record captures a moment, not a species, a breath, not a life. And like any snapshot, it becomes more precious as the moment it captures recedes further into the past. Let us sit with this image for a moment. Two small machines, identical twins, born in the same room in Pasadena, launched from the same pad at Cape Canaveral, carrying the same cargo of instruments and cameras and golden records, setting out on the same mission but taking different paths through the solar system, past different combinations of worlds, making different discoveries, experiencing different failures and triumphs. And now, finally, both in interstellar space, heading in different directions, diverging at a rate of several miles per second, growing farther apart with every passing moment, sailing into different futures that no one on Earth will ever witness. It is like a story about siblings. Two children raised in the same home who grow up and move to different cities, different countries, different lives. They share the same memories of childhood. They carry the same family name. They have the same parents, the same origin, the same fundamental nature. But their lives diverge. Their paths separate. And eventually, they are so far apart that they can no longer hear each other, can no longer even imagine where the other one is or what they are experiencing. They are connected only by their origin, only by the fact that they came from the same place and carry the same message in their hearts. The Voyagers are like that, connected by origin, separated by destiny. Two expressions of the same hope thrown in opposite directions into an ocean that is dark and vast and silent. And what about us? What about the species that built them, that launched them, that followed their journeys for decades, that named them and nursed them and mourned each instrument failure and celebrated each discovery? What will become of us in the time it takes for the Voyagers to reach the stars? No one knows. No one can know. The future is as opaque to us as the interstellar medium is to our telescopes. We cannot see through it. We cannot predict it. We can only guess, and our guesses, colored by hope and fear, and the limited perspective of a species that has existed for only a few 100,000 years, are almost certainly wrong. But here is what we can say. Whatever happens to us, whatever becomes of our species, whether we spread to other worlds or remain on this one, whether we endure for millions of years or vanish in the next few centuries, the Voyagers will carry a record of who we were, not who we will be, not who we wish we had been, but who we were in 1977, when a small group of people assembled 2 machines in a room in California and loaded them with the best of what we had to offer: Bach and Beethoven and Chuck Berry, whale songs and thunderstorms and the laughter of children. Greetings in 55 languages from a world of 7 billion people who could not agree on much but could agree on this: that it was worth saying hello to the universe, that it was worth sending a message, even if no one would ever read it, that the act of reaching out was, in itself, an answer to the loneliness that haunts every thinking being who has ever looked up at the night sky and wondered if anyone else was looking back. There is a passage in Carl Sagan's book Pale Blue Dot that captures the spirit of the Voyager mission better than any other words I know. Sagan wrote it about the photograph that Voyager 1 took of Earth from the edge of the solar system, that tiny pale blue speck barely visible against the darkness. But it applies equally to the entire Voyager enterprise, to the audacity of sending 2 small machines into the infinite. It has been said, he wrote, that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. Sagan understood something that many people miss. The Voyager mission was not just about exploring the outer planets. It was not just about science. It was about perspective, about seeing ourselves from a distance, about understanding viscerally and emotionally, and not just intellectually, how small we are, how fragile, how precious, and how remarkable it is that beings so small and so fragile could build machines that travel between the stars. Tonight, as you lie here, 2 machines are flying through interstellar space. They are roughly 11.5 billion and 12.5 billion miles from Earth, respectively. They are traveling at 10 and 15 miles per second, heading in different directions, growing farther apart and farther from home with every heartbeat of your sleeping body. They will be out there for a very long time. Long after you and I are gone. Long after everyone we have ever known is gone. Long after the languages on the golden record have evolved beyond recognition and the nations that spoke them have dissolved into the river of history and been forgotten. Long after the buildings where they were built have crumbled, and the launch pad where they began their journey has been reclaimed by the Florida swamp. Long after the sun has consumed the inner planets and collapsed into a white dwarf, a cooling ember where a star once burned. The Voyagers will still be out there. 2 small machines, 2 golden records, 2 messages in 2 bottles, sailing through an ocean without shores. And perhaps, in some unimaginably distant future, one of those bottles will wash up on a shore that we cannot envision. Perhaps some form of intelligence, carbon-based or silicon-based or something we cannot imagine, will find one of these small, battered machines drifting through its stellar neighborhood. Perhaps it will examine the machine with instruments we cannot conceive of, puzzling over the metal alloys and the corroded electronics and the golden disk in its protective cover. Perhaps it will figure out the instructions on the cover. Perhaps it will build a device to play the record. And perhaps, in a place so far from Earth that the sun is not even visible, in a time so distant from now that the word year has no meaning, something will hear the first notes of Bach's Brandenburg Concerto, or the sound of rain on a summer afternoon, or the voice of a 6-year-old boy saying hello from the children of planet Earth. And perhaps, for one brief moment, across the gulf of stars and time and silence, A connection will be made. A message sent by a species that no longer exists will be received by a species that the sender never imagined. And the universe, which is vast and cold and mostly empty, will be a little less lonely. Or perhaps no one will ever find them. Perhaps the Voyagers will drift through the galaxy until the stars themselves burn out, carrying their cargo of music and greetings and brainwaves through an emptiness that stretches to the end of time. Perhaps the golden records will never be played. Perhaps the music will never be heard again. Perhaps the message will be as permanent and as silent as the stars. But that is not the point. It was never the point. The point was never whether someone would find the message. The point was that we sent it. The point was that a species, barely out of the cave, looked up at an ocean of darkness and light that stretched in every direction for billions of light years and said, "We are here. We made music. We fell in love. We wondered about the universe. And we wanted someone to know." That is the story of Voyager 2, and of Voyager 1, and of the species that built them. A story of ambition and fragility, of precision and luck, of silence and song, of two small machines that carried the best of us into the dark, and that will carry it there long after the last of us has gone. Let that thought carry you into sleep tonight. Let the image of two golden records, spinning silently through the starlight in different parts of the galaxy, be the last thing in your mind as you drift away. They are out there, right now, both of them, moving forward, always forward, into the unknown, into the endless, patient, beautiful dark, and they carry us with them, the sound of our rain, the echo of our music, the warmth of our laughter, the quiet wonder of a woman thinking about love while a machine recorded her brainwaves. They carry all of it. They carry us. And in that way, we are already among the stars. We have always been among the stars. The night is quiet now. Your breathing has slowed. The thoughts that raced through your mind at the start of this journey are fading, softening, dissolving into the warm fog of approaching sleep. The room is dark. The world is still. And somewhere out there, beyond the roof, beyond the clouds, beyond the atmosphere, beyond the moon and the planets and the icy edge of the solar system, two small machines are flying through the dark. They are not thinking. They are not feeling. They are not aware that they carry the hopes and dreams and music of an entire world. They are just moving, quietly, patiently, endlessly. Two bottles in the cosmic ocean. Two messages from a world of oceans and mountains and sunsets and snow. Two small golden circles carrying the voice of a child, the song of a whale, the music of Bach, and the brain waves of a woman in love. They are out there, and they will be out there for a very, very long time. Sleep well. The stars are waiting, and so are we. Good night.